3I Atlas did not enter the solar system. The solar system ran into it. We know this because Atlas never slowed down. Its trajectory was hyperbolic, the kind that cannot be captured, bent, or decelerated by the sun. Objects that truly arrive always are. That behavior rules out the obvious explanations. It is not technology, it is not propulsion, and it is not intent. When motion looks impossible, the mistake is usually not in the object, but in the frame we use to measure it. So the real question is not where Atlas came from, but how far physics allows us to follow an object that refuses to slow down. Physics answers that question with a hard limit, and that limit appears the moment we try to respond. On July 1, 2025, the Atlas telescope in Chile registered the anomaly. It appeared as a faint streak against the constellation Sagittarius, but the telemetry told a violent story. The object was cutting through the inner solar system in a way that violated every intuitive expectation of local orbital motion. To understand the scale of this event, we must look at our own best effort. Voyager 1. The fastest spacecraft ever launched by humanity has spent nearly half a century clawing its way out of the sun's gravity well. It utilized perfect alignments of Jupiter and Saturn, stealing momentum from gas giants to achieve a velocity of 17 kilometers per second. It is the pinnacle of human engineering. 3I Atlas broke that record without trying. It entered our neighborhood maintaining a hyperbolic excess velocity of 61 kilometers per second, more than 3 times the speed of Voyager. It did not require gravity assists. It did not wait for planetary alignments. It simply ignored the gravitational toll roads that govern our spacecraft. In the immediate aftermath of the discovery, the question was inevitable. Can we catch it? The answer lies in the cold mathematics of the delta-v barrier. In spaceflight, velocity is a currency, and Atlas is behind an energy paywall we cannot afford. To intercept this object, a spacecraft would not only need to reach its location, it would need to generate enough thrust to match that 61 kilometers per second vector. With current chemical propulsion, that is a physical impossibility. We are standing on a station platform watching a bullet train scream past, armed only with cameras. We cannot capture it, we cannot touch it, but we can observe the wake it leaves behind. And the first piece of evidence, the trajectory itself, is already suggesting that this is no ordinary rock. Because in orbital mechanics, how something moves matters far more than what it is made of. If the trajectory of 3I Atlas is treated as forensic evidence, then the geometry is our first clue. And the geometry is disturbingly precise. In a random universe, interstellar debris should arrive isotropically, meaning it should come from anywhere. A rock ejected from a distant star system has no reason to respect the architecture of our solar system. It should dive in from the galactic north or slice up from the south, cutting through our orbital plane at a steep, chaotic angle. That is what we saw with 1I Oumuamua, which tumbled in from above the plane like a stone dropped into a pond. Atlas did something different. It slid in through the side door. The object's trajectory was retrograde, moving against the flow of planetary traffic, but its inclination relative to the ecliptic, the flat dinner plate, where Earth and the other planets reside, was only 5 degrees. It didn't just pass through our system. It skimmed the ecliptic plane with the accuracy of a needle threading a groove. This specific flight path allowed Atlas to perform a tour of the inner solar system's most valuable real estate. It passed through the orbital neighborhoods of Venus, Earth, and Mars in sequence. It did not experience a close encounter in the gravitational sense. It didn't swing around a planet to steal momentum, but it occupied the same narrow band of space that harbors our system's habitable zone. In orbital mechanics, this is known as a low perturbation entry. By staying within the plane but moving at high velocity, Atlas minimized the gravitational scattering effects of the planets. It was a clean entry. To a ballistic analyst, a trajectory that maximizes planetary proximity while maintaining a stable flight path looks less like a random tumble and more like an injection maneuver. That resemblance, however, can emerge from geometry alone, without any control or intent. Proponents of the artificial origin hypothesis immediately flagged this alignment. They calculated the odds of a random object coinciding with the ecliptic plane to within a few degrees at roughly 1 in 500. In the court of law, a 0.2% probability might be enough to warrant suspicion of intent. but in the court of astrophysics probability is a tricky witness. Before we attribute this precision to alien engineering, we must run the data through a critical filter, observational bias. The universe is dark and our eyes are small. We do not watch the entire sky with equal vigilance. The majority of our planet-hunting and asteroid-warning telescopes like Pan-STARRS or the Atlas network that discovered this object are programmed to stare specifically at the ecliptic plane. Why? Because that is where the rocks that might kill us near-Earth objects are located. We are like a drunk searching for his keys under the streetlight, not because he lost them there, but because that is the only place he can see. If 3I Atlas had approached from the galactic pole, remaining high above the plane of the planets, it is statistically likely that we never would have seen it at all. We detected this object specifically because it skimmed the ecliptic. The coincidence of its trajectory may simply be a reflection of our own tunnel vision. Furthermore, we are dealing with the law of large numbers. The Milky Way is a chaotic shooting gallery containing billions of rogue objects. Even if a specific trajectory is a 1 in 500 rarity, nature rolls the dice billions of times every epoch. A statistical anomaly is not proof of design. Often it is merely a statistical inevitability waiting to be observed. However, dismissing the anomaly entirely would be intellectually dishonest. The alignment exists, the velocity is real. And while the where and how of its arrival can be debated through statistics, there is another piece of evidence that cannot be explained away by bias. When viewed from within the solar system, a trajectory this clean looks intentional. But before we accuse design, we have to ask a harder question. What if it only looks that way because we are moving? To find the origin of 3I Atlas, we must stop looking at the speedometer and start looking at the map. From our vantage point on Earth, Atlas appears to be a hypervelocity intruder tearing through the neighborhood at 61 kilometers per second. That speed is the primary reason the alien probe hypothesis gained traction. In our human experience, high speed implies intent. It implies an engine, a destination, and a schedule to keep. But in astrophysics, velocity only has meaning within a chosen frame of reference. We must shift our frame of reference from the heliocentric frame centered on the Sun to the galactocentric frame centered on the Milky Way. The Sun is not a stationary lighthouse. It is a projectile orbiting the center of the Milky Way at approximately 220 kilometers per second. We are moving near the local standard of rest, the average motion of stars in our local spiral arm. When we subtract the Sun's massive orbital velocity vector from Atlas's trajectory, the picture flips entirely. In the galactic frame, 3I Atlas is not racing, it is lagging. Its velocity relative to the galactic center is significantly slower than the Sun's. It is not overtaking us, we are overtaking it. The object was drifting through the void, minding its own gravitational business, when the solar system encountered it like a fast-moving vehicle overtaking a much slower one. This kinematic inversion changes the profile of our suspect. A scout ship launched by an advanced civilization would likely utilize the rotational velocity of the galaxy to boost its speed or match the velocity of its target system to effect a capture. Atlas does neither. Its vector is chaotic, unconnected to the orderly rotation of the spiral arms. It moves like something that has been tumbling through the dark for a very, very long time. This is not a precision strike. It is a galactic traffic accident. So if Atlas is just drifting, where did it drift from the forensics of its motion point to a specific and ancient neighborhood? The Milky Way is not a uniform flat disk. It has architecture. We live in the thin disk, a region rich in gas dust and young stars where orbits are orderly and circular. But surrounding us, extending thousands of light years above and below the plane, is the thick disk. The thick disk is the galaxy's old city. It is populated by ancient stars, the survivors of the Milky Way's violent youth. The orbits here are not neat circles, they are eccentric, inclined, and chaotic. They plunge through the galactic plane at steep angles and drift with lower rotational velocities than the modern thin disk stars. Atlas's kinematic signature matches this profile perfectly. Its retrograde inclination, its low rotational speed, and its deep plunge through the ecliptic are all classic hallmarks of a thick disk origin. This gives us a terrifying sense of scale. The stars in the thick disk are estimated to be between 8 and 10 billion years old. This means 3i Atlas is not just a visitor from another star. It is likely a visitor from another epoch. It may have been ejected from its home system billions of years before our sun even ignited. It has spent eons playing galactic pinball, being nudged by the gravity of passing stars drifting through the void, while the Earth formed, while life emerged, and while civilizations rose and fell. It is a remnant of a long-dissolved system, a piece of debris from a forgotten star system preserved by the absolute cold of interstellar space. This theory provides a robust alibi against the artificial hypothesis. The chaotic slow motion is exactly what we would expect from a natural object ejected in the early galaxy. But alibis in astrophysics must be corroborated. If Atlas really is an ancient fossil from the thick disk, it should look the part. Its physical body should carry the scars of time, and its chemical composition should reflect the recipe of the universe as it existed 10 billion years ago. If Atlas is ancient, then its motion is only half the story. Age leaves fingerprints, and physics knows exactly where to look. Trajectory tells us where an object has been, but only chemistry can tell us what it is. To get that data, we needed a catalyst. We needed physical conditions that would make its composition observable. Fortunately, the trajectory of 3i Atlas brought it within 1.4 astronomical units of the Sun, just inside the orbit of Mars. In physical terms, this was a thermal forcing event. As the object approached perihelion, the exponential increase in solar radiation acted as a stress test. The surface temperature spiked, driving rapid phase transitions within the object's surface layers. Ancient ices frozen for billions of years near absolute zero began to sublimate, turning instantly from solid to gas. This outgassing created a coma, a fuzzy envelope of dust and vapor surrounding the nucleus. Unlike the metallic, inert silence of 1i Oumuamua Atlas, was emitting material into space, producing measurable spectral signals. This was the moment the James Webb Space Telescope had been waiting for. Turning its near-infrared spectrograph toward the intruder, humanity began to dissect the light passing through that cloud of gas. Every element in the universe absorbs light at specific frequencies. By measuring which colors were missing from the spectrum, astronomers could reconstruct the molecular recipe of the object. The results were baffling. They presented what is now known as the water puzzle. The spectral signature showed strong evidence of water. Clear absorption lines for hydroxyl and water vapor indicated that Atlas was undeniably an icy body, a comet. But as analysts scanned for other standard cometary ingredients, the signal flatlined. There was a glaring absence of cyanogen and other carbon chain molecules. In our solar system, comets are dirty snowballs, a chaotic mix of water ice dust and carbon-rich organic compounds. When they heat up, they glow with the spectral lines of carbon. 2i Borisov, the second interstellar visitor, looked exactly like this. It was chemically indistinguishable from our own local comets. Atlas was different. It was effectively pure. It was releasing vast amounts of water, but it was chemically depleted of carbon. To a layman, this might seem like a trivial detail. To an astrochemist, it was a smoking gun. The missing carbon anomaly is not evidence of artificial purification. It is evidence of extreme age. It confirms the thick disk theory with chilling precision. To understand why, we have to look at the periodic table as a timeline. In the early universe, shortly after the Big Bang, there were only hydrogen and helium. Heavier elements, what astronomers call metals, had to be forged in the nuclear furnaces of dying stars. Oxygen is created relatively quickly in massive stars and ejected via supernovae. Carbon, however, takes longer to accumulate in the galactic ecosystem. It is primarily produced by low to intermediate mass stars that live longer lives before shedding their layers. This means the chemical composition of a star system depends entirely on when it was born. Stars that formed recently, like our Sun, belong to population 1 and formed from gas clouds rich in recycled carbon, iron, and silicon. Stars that formed in the galaxy's youth belong to population 2 and formed from a cleaner, simpler mix. They are oxygen-rich but carbon-poor. The spectral fingerprint of 3i Atlas matches the profile of a population 2 relic. Its low carbon-to-oxygen ratio suggests it coalesced in a protoplanetary disk around a metal-poor star roughly 8 to 10 billion years ago. This changes our perception of the object entirely. Atlas is not a spaceship, it is a frozen archive. It is a sample of the primordial soup from which the Milky Way galaxy evolved, preserved in the deep freeze of interstellar space and delivered to our doorstep. It carries within its ice the chemical conditions of a time before Earth existed, before the sun ignited, perhaps before the Milky Way had even settled into its current spiral shape. The alien hypothesis crumbles under the weight of this data. We don't need advanced engineering to explain the water-rich carbon-poor composition. We just need time. Deep geologic cosmic time. The chemistry suggests nature, not engineering. The trajectory suggests an ancient accident, not a targeted mission. The forensic case for a natural origin is strongly favored, but not yet closed. But physics has one final test to administer, a test of structural integrity that will occur where our telescopes cannot follow. Chemistry only speaks when we can observe, and the universe is about to take our eyes away. Following the thermal forcing phase, the investigation hit a physical wall. It wasn't a lack of interest, it was a lack of geometry. As 3I Atlas rounded the Sun in late 2025, swinging through its point of closest approach, Earth was positioned on the exact opposite side of the solar system. In orbital mechanics, this event is known as superior solar conjunction, when the Sun lies directly between Earth and the target. To an astronomer, it is effectively a blackout. For 6 critical weeks, the line of sight between Earth and Atlas passed directly through the solar corona, the superheated plasma atmosphere of the Sun. This environment is a chaos of charged particles and magnetic turbulence. When radio waves or optical light attempt to pass through it, they suffer from extreme scintillation. The signal is scattered, phase-shifted, and buried by plasma turbulence. The signal-to-noise ratio dropped to near zero. We were effectively blinded. This blind spot is the stuff of thriller novels for a reason. If 3I Atlas were an intelligent probe, this would be the tactical moment to act. Hidden behind the overwhelming glare of the Sun, masked by the electromagnetic scream of solar flares, a spacecraft could perform a course correction burn without being detected. It could pivot its sensors, transmit a high-density data burst to a relay station, or alter its velocity vector to intercept a new target. We would see none of it. We could only wait. During this blackout, the Green Bank telescope and the Deep Space Network kept listening, hoping to catch a piercing narrowband signal, cutting through the solar static, a techno-signature that would defy natural explanation. But the monitors showed only the random roaring baseline of the Sun. No artificial signal was detected. The object entered the dark room, and for 40 days, physics held its breath. In early January 2026, 3I Atlas emerged from the glare, racing outbound at maximum velocity. The data link was re-established, and astronomers immediately ran the final stress test checklist. The perihelion passage had been a trial by fire. The results would determine the verdict. Test 1. Structural integrity. Comets are fragile things. They are often loosely bound aggregates of ice and dust held together by gravity so weak you could jump off their surface. When subjected to the intense tidal forces and thermal shock of a solar flyby, they frequently shatter. Comet C 2019 Y4, known as Atlas, a solar system native, disintegrated under similar conditions in 2020. If 3I Atlas had fragmented into a cloud of debris, the artificial hypothesis would have died instantly. Spaceships don't crumble under thermal stress. Piles of rubble do. Result: Atlas emerged intact. It lost mass, certainly, but its nucleus survived. Its nucleus remained coherent. But survival alone does not prove intelligence. It proves material strength. Test 2. The rocket effect. This is the most critical forensic measurement. As we tracked the outbound trajectory, we looked for non-gravitational acceleration. When a comet heats up, jets of gas shoot out from its surface. This acts like a thruster, pushing the comet slightly off its predicted gravitational path. This is the rocket effect. If the acceleration is chaotic or correlates perfectly with the brightness of the coma, more sunlight leads to more gas, which leads to more push. It is natural. If the acceleration is steady, uncorrelated, without gassing, or directed in a way that fights solar gravity, it is suspicious. This was the anomaly that made Oumuamua so controversial. It accelerated without a visible coma. The post-conjunction astrometry for Atlas is now coming into focus. The object is deviating from a pure gravity arc, but the math is boringly consistent. The push it is experiencing matches the thermal model of sublimating water ice almost perfectly. The vector is radial pushing directly away from the Sun, exactly as expected for a venting comet. Test 3. The transmission. The SETI Institute has completed its initial sweep of the post-perihelion data. No narrowband beacons, no leakage radiation, no mathematical prime numbers encoded in the static. The verdict. The checklist has so far returned no evidence of artificial behavior. The object survived the heat-vented gas like a comet, pushed itself away like a comet, and remained silent like a rock. The alien probe hypothesis, while mathematically possible due to the trajectory alignment, has failed to produce a single piece of corroborating physical evidence. Occam's razor is sharp and it cuts deep. It tells us that we do not need to invent a civilization to explain this object. We only need the laws of thermodynamics and gravity. But as 3i Atlas fades into the darkness, racing toward the edge of the system where our telescopes can no longer resolve it, we are left with a lingering, uncomfortable realization. We solved the what, but we are powerless to change the outcome. For 6 weeks, the data went dark. When it returned, only one question remained. Did the object survive physics itself? It did, and now it is leaving. As of January 2026, 3i Atlas is already crossing the orbit of Jupiter, racing outbound into the dark. By the time you watch this, it will be millions of kilometers further away than it is right now. Every second, the light travel time increases, the data stream thins, and the resolution of our instruments degrades. The primary observation window has effectively closed. The verdict of the scientific community is leaning heavily toward the natural explanation. The chemical fingerprints point to a primordial origin. The acceleration profile points to cometary sublimation. The silence points to an inanimate object. Occam's razor suggests that Atlas is simply a wanderer, a shard of the early galaxy ejected from a dying star system billions of years ago, which happened to cross our path through statistical chance. But chance is a heavy word. The statistical improbability of its trajectory, that clean, ecliptic skimming entry, remains a stubborn splinter in the mind. Not because it implies intent, but because it exposes how incomplete our sampling of interstellar space still is. While we can explain it away with observation bias, we cannot fully erase the feeling that we have missed something fundamental. This is the epistemic limit, the hard boundary of our knowledge. We are limited by our sample size. In the entire history of astronomy, we have cataloged only 3 interstellar visitors: 1i, Oumuamua; 2i, Borisov; and now 3i, Atlas. Trying to build a theory of galactic population from 3 data points is like trying to map the entire ocean by looking at 3 cups of water. We are not yet masters of this domain. We are barely conscious of it. Ultimately, the story of Atlas is a lesson in cosmic humility. It reminds us of the delta V barrier that keeps us tethered to our home star. We built the fastest machines in history, yet we stood helpless as a piece of the universe's history screamed past us at 61 kilometers per second. We could not chase it. We could not capture it. We could only watch. We may never know for certain where it came from or exactly what star system birthed it in the dawn of the Milky Way. But its passage has proven that the space between stars is not empty. It is full of remnants, full of history, and full of physical records waiting to be interpreted. This analysis represents the forensic limit of what we know in 2026. The universe, however, is under no obligation to conform to our current understanding. The answer to the mystery of 3i Atlas does not lie in any single observation. It lies in the data we are still learning to decode and in the next visitor which is already on its way.